computer. All right, nice. Yeah, that I know people have been asking about that, so hopefully that'll be helpful. Okay, all right, Stefan here, hang on. You asked, oh wait, no, I don't want to do that. You asked, I'm gonna do that. No. About number, and I lost track, but let me just find the questions here first. All right, so I'm at the class. All right, so chapter 24, what number again?
Number 29A.
29A, all right. So 29 says, consider a thin spherical shell of radius 14 centimeters with a total charge of 32 microcoulombs distributed uniformly on its surface. Find the electric field at A, okay, and then B. Now you only asked about A. I'll do both if you want, just for completeness, and maybe somebody wants to see it in the video, but I'll start with A. And
Okay.
will give me a chance again to try this like we did last week. I liked what it worked. I hope you guys did too. Let me switch my screen to share on my iPhone. And then let me turn my iPhone on and do a screen sharing. And it's connecting here, Bluetooth. Everything's looking good so far. Okay, good. See that. Whoops. Try my face in here. Oh, bummer, I can't really get my keypad without.
Professor, quick question about the actual problem set. Number 50 looks like it's crossed out. Is that just like a copying error, or is it? Should we do number 50, I guess, or is it intentionally crossed out?
Let me look here. 50.
Yeah. On chapter.
Oh, you should do kind of a classic one. Yeah, it's a good question. Why that scribble there? No, do that one.
Yeah, I was just checking.
Yeah. Okay, so let's come back here and I'll just double check by asking you guys. Can you see my iPhone camera? I know it's a little narrow.
Yeah, I can see it.
Okay. All right, so I'll put here chapter 24, number 29 at the start here. Maybe I'll even put page 1. I don't know if this will go quite to 2 pages, but I will say that the big picture of this chapter was this. Gauss's law. He discovered a nice little mathematical pattern that connects the electric field to what I would call something mathematical, the flux. And so this integral of the electric field over an area is the flux. Okay, so without going into a lecture again on the flux, let's do the problem. And so 29, if I was drawing a picture, would I guess look something like this in 2 dimensions. There's my sphere. I won't try to draw a 3-dimensional sphere. But this is where the charge is, and so I'll just kind of put a bunch of pluses. They say the total on it is the 32 microcoulombs. And the key then is to try to solve this equation and manipulate around the math so you can get the electric field. And the technique is what we call a Gaussian surface. And so if you let me draw a Gaussian surface that is at a radius of 10 centimeters, because they say that the sphere is 14 centimeters. In other words, this is inside of the sphere.
Right.
Okay. So the magical step is actually over here on the right-hand side that says the amount of charge enclosed in that surface is 0.
Okay.
So that means the right-hand side, if we do this integral, first the dot product, which would be the EDA cosine of phi. And if you got this out of the the lecture, the symmetry argument would be that the electric field would have to be radially outward. So the normal would have to be and the normal's radial outward. So the angle's got to be 0, and cosine of 0 is 1.
Right.
And also the symmetry argument is the electric field would have to be a constant. And it sounds like you're good with the rest of it, but eventually then you just come up with electric field equal to 0. So that's the math of it, and why I have your attention. I'll say now, here's the physics of it. Maybe a different color might help it stand out, but if I were to pick some point on this Gaussian surface, some point that is 10 centimeters from the center, and the question is, what's the electric field on there? And the math just told me it was 0. But to understand it conceptually, I'm going to just draw 2 intersecting lines at that point where I want to find the field. And that chops this charge into 4 pieces. And we know the electric field at this point is made then from these charges. So let's look at these 4 pieces and see what we come up with. And I'll call this top piece number 1 and the bottom number 2. You look at them, they got the same size, the same angle, and so this top one would make an electric field somewhere kind of in a downward direction, maybe a little more towards this way because of more over here, but this would match it here. And so those 2 would be equal and opposite and cancel off.
Okay.
And then the harder one to see is that these 2 would also cancel off. It's, I think, hard to see that because you're closer to what I'll call part number 3 compared to part number 4. And we know that the electric field is stronger the closer you get. But on the other hand, as you get closer, the amount of charge is less than way over here.
Okay.
And since it's a sphere, and this is the magical step, it's a sphere, the area on a sphere is this 4 pi r squared. In other words, the area, that is the amount of charge over on surface 4 compared to surface 3, has gone up by an r squared. But the equation for the electric field decreases by that same proportion. And so surprisingly, or maybe not now that we give it some deeper thought, the amount of field from 3 is equal to the amount of field from 4. More charge on 4, but further away. And more charge by the exact same proportion that the field gets weaker. And so with all those put together, gives you a field of 0 on the inside.
Okay, thank you.
Yeah, you bet. You bet. All right, you know what? I'm going to change my screen view, I think. Oh, I should do it over here on my other one here. All right, so I can see everybody. Let's just shrink that up, see who's all here. And also put the chat room here. All right. Hey, that 121, who was it? Rylan, you still here? I lose you? Oh, bummer. Okay. I hope he comes back. All right. Who was next here? Anybody want to jump in?
I think Quinn had a question in the chat, but I also have a question.
Yeah,
Oh, Quinn. Okay, so fairness to Quinn, he put it in the chat, and I think I saw him on real early. So here we go. A couple questions back. Oh yeah. You were. I'm sorry, Quinn. You were the one that we were having some audio trouble with here. Okay. A couple questions about the lab. I was confused about how to describe the graph properly, as well as to interpret the slope. Oh, good. Yeah. All right. So let's see. I guess I'm still sharing my screen. And you have 3 graphs in that lab. One is distance versus time. Let me get rid of my red pen. And it looks something like this. You had a third graph that was velocity versus time, looked something like this. And then you have a third graph that is distance versus time squared and looks something like that. Okay, now your first three questions were about this graph. And just for clarity, I know you didn't ask all of this, but I'll just take a moment to say, the first question says, okay, what is the shape of it? And there's a lot of ways of saying that, but what they want you to really say, because you need to notice this for the next set of questions, is that it is a curve, so it's not a line, and it's concave up. So the best answer I could say for question number one is say it's a curved concave up. Because when you go to question two, I'm trying to remember now question two. Question two is,
I was asking how to interpret this.
right, how do we interpret the slope? Which that gets really to your question. So let me just remind you of your math class. Slope is the rise over the run. And the rise is what you plot on the vertical axis. And the run is what you are plotting on the horizontal axis. So this would be the, I'll guess, the change in distance over the change in time. And so if we take our knowledge from our math class and apply it to what we're doing here in the lab, and then if we look at that definition from our lecture, that is the velocity or the speed of the object. So question number two, they're trying to just say, hey, it would be the velocity.
Okay.
Yeah.
Okay.
So if you then, for question number three, where it says, what is the slope telling you? If you look at the slope down here at the beginning part, the slope's kind of small, then it gets bigger, and then it gets really big. And since the slope is the velocity, this would be telling me the velocity is increasing, getting bigger, 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 bigger. And so the best answer for question number three is to say that this graph is telling me that falling Bob has an acceleration.
Okay. Acceleration.
So that's how those three questions go together. The first one, and I'll just repeat since I can't hear your audio, but I think you got it. The first one is, this one is saying the concave up, which then, since slope is giving you velocity, then this graph is telling me that the velocity is increasing, and that is it's accelerating. And so those are the three questions. Number three is the big picture. This graph would say that I have just proven that this falling object from the lab is accelerating.
Okay.
So if that made sense, let's look at the next three. The next three are really saying the same thing. The first one, but it's looking at this graph here. It's saying, now let's look at velocity versus time. So question number, I guess it would be 4, 5, and 6. 4, 5, and 6 say this. 4 says, what's the shape of it? Okay, well, I would just say it's a line. Okay. Then 5 is saying, what does the slope give you? And if you come back to the same logic, starting with math, the slope is the rise over the run. In this case, though, we're plotting the velocity on the vertical axis. So that'd be change in velocity and over change in time. And so that is the acceleration. And so the best answer to question number 5 is the slope for this type of graph gives me acceleration. And hopefully you see that same kind of logic in step 2. See, step 2, the slope gave us velocity, but in step 5, because we're looking at a different graph, the slope gives us the acceleration. So then in step 6, it says, okay, what does this tell us? And so if you put together a line with the slope is the acceleration, let's look at that. That would say that the slope right here at the beginning and the slope right here at the middle and the slope right here at the end all have the same slope. That's what you mean by the word it's a line. So this would tell me, and this is what they're trying to get at in step 6, this would tell me that the falling object had a constant acceleration. And that's really what they're looking for. So I would say the evidence of your lab has done 2 things. The first 3 questions right here told me that the falling object is accelerating. The next 3 questions tell me that the falling object has a constant acceleration. That's why question 7 says, measure this slope so that we could actually then find the value of this constant acceleration. And if I remember my numbers right from helping another student earlier in the week on this, if you take the last data point and the first data point in your chart, and for some reason I want to say the first velocity was 45 and the time was 12/30ths of a second. That's the run. I can't remember what we got in the video for that top one, but I'm pretty sure I remember, and I'll go back and redo it if you want to look up the video, but this came out to be 960 centimeters per second each second for the slope of that. And I'll give you a little warning here that sometimes it's easy to forget that the run is 12/30ths of a second, and students forget this. So instead of getting,
flip it and multiply it.
I'm sorry?
So you just flip it, so it's 12/1/30th, so you just flip it and multiply it.
Yeah. So the math would look something like this. You would have your change in velocity here, and when you divide by 12/30ths, the easiest way to do a division, but you could actually turn that into a decimal in your calculator if you're a little weak with your fractions, but you flip it and multiply. So go 30/12.
Okay, perfect.
And that's why you might have, many students do, forget that the time is in 30ths of a second and they just have a 12. And so their answer is off by this 30. See, because this divided by this would be, I divide that by 30, that's 32. Yeah, so a lot of times I will get a 32 for the slope. That's because they.
So wait, where did the 960 come from? I was just a little confused on that.
Oh, all right. So the 960. I'm just going to make sure my sound's up all the way. Okay. So coming back to the 960, it's this graph here. And since it got kind of messy, I'm going to grab a new piece of paper. All right. So starting with a new piece of paper here. Here's the velocity versus time. Your graph looks something like this. And like I said, your first point, I think, is at a 1, and your last point is at a 13. But these are in 30ths of a second. And so this is the 12/30th of a second. So that's the run. This point is 45. And this point, and this is the one I can't remember. It's back in the video. Maybe I can do a reverse engineering knowing that the slope is 960. So if I multiply that by 12/30, if I did my calculation right, you should have gotten 383 in that big chart. Is that 384? Sorry, does that look familiar?
For 13. At 13.
So yeah, the speed at 13 or at 12.
Oh, I got 169, but I feel like I must have done something wrong.
So your
380,
fastest
yeah.
speed, you think, did you get 45 for the first speed?
Oh, okay. You're talking about velocity. Okay, yeah. My fastest velocity difference between the 2 seconds was 429, and then the one before that was 393. Does it make any sense?
Yeah, I'm wishing I had my notebook here at home. I wrote all those down when I did the video, and I'd have to go back and look at the video. 384 minus 45 divided by 12/30. Oh, I'm sorry. I did my math wrong. I think let me try that again. I think maybe you got it right. I think it's supposed to be 384 plus the 45, 429. Yeah, that sounds familiar. What'd you say you got?
Yeah, it was 429.
Okay, all right. Sorry for misleading you. All right, let me try this again. All right, so your highest speed should be this 429, so that's good. And then this one I did on the video, this was the 45. And so to get your slope, which is the rise over the run, you take the difference of these two. So how high did it go up? 429 minus 45. How much time did it travel by? 13/30 of a second minus 1/30 of a second. So the rise becomes 384. The run becomes 12/30. This then becomes 384. And if we flip and multiply, grab a calculator, 384 times 30 divided by 12, there it is, 960 centimeters per second squared is the main part and the answer to number 7.
Okay, and since that's not like, and since that's a large number, like that's reasonable.
And then that's actually a perfect number, because in class and in the book, I've been saying that the acceleration of a falling object is 9.8 meters per second squared, which is the same as 980 centimeters per second squared. So this number is very close. What we actually measured is very close to what you've been told in class. And so that's the answer they want to give you in number 8 when they say, is this a good number? Is this reasonable? Does it make sense?
Okay, awesome. Okay, that makes everything make way more sense. Thank you for that.
All right. You good?
And then the last one's just like comparing the two of them.
Oh yeah. Let me maybe I'll draw it again because this first page got kind of messy. But the very last question, question 9, they said, look at this graph, distance versus time squared. And so let me redraw that one. So here's distance, and here's time squared. And they want you to notice it's a straight line. So question 9 actually has 2 parts to it. The first part says, describe the graph. Okay, so linear, it's a line. And interpret the meaning of it. And anytime we have something that's a line, the fancy mathematical word is that they are proportional.
Okay.
So they want you could either put it in words that said distance is proportional to time squared. That would be one way to answer it. Or you could put it in math form, which says this: distance would then be equal to some unknown number, which would be the slope of that. So we could actually measure it, but they didn't ask us to. So I'm just going to put slope multiplied by time squared. And the question stopped there, but I'm just, as long as I got your attention, go one more step. Because in class, we learned this equation, that this would be the equation for an object that is dropped from rest, and that's what we did in the lab. So not a surprise that what we measured in the lab matches what we've been talking about in class. So if I were to measure the slope of this one, and again, you're not asked to do it, but if I did, I would expect to get 1/2 of the 980. So I would expect the slope here to come out to be that 1/2 of 980. Although we did the lab and we got 960, so that would be more like 480. So I bet if you measured the slope of this, you would get it to 480. So if there was a question 10 would have said, hey, measure the slope of that and see if the slope is 1/2 the acceleration as predicted by our discussion in class.
Okay, perfect. Thank you so much for all that.
Good. All right. Rylan, I think you came back. You're muted.
Howdy.
Howdy. All right. You had a good question for me. One that was from 121, right?
Yeah, from 121, it was just a related rates thing that I just couldn't quite figure out how to do, and we haven't really gone over it yet. So should I just tell you the problem? Should I show it to you? What's the best way to get about it?
You start with telling me. Let's see if I can make sense out of it.
Okay, let me pull it up. So it's a related rates with a spherical balloon is the problem.
Okay. Okay. I think I know where this is going. Go on.
Okay, so we've got the radius of the balloon is r.
Okay.
The radius of the balloon is increasing at a rate of 0.522 centimeters per second.
0.522 centimeters per second. Okay, go on.
And the volume of the balloon, sorry, I clicked back to you. The volume of the balloon is increasing at a rate of 666 centimeters cubed per second.
666 cubic centimeters per second.
And so
Okay.
that's sort of the phrase that's sort of the way it's phrased. That's all the information I'm given. I'm assuming that I'm supposed to find big R there, you know?
So the question, just let me confirm, the question says, what is the rate of, wait, what was the
So the
question?
weird thing about the way that Doug's homework system works is there isn't really a question. There's just a variable that's not there, right? So it just, the one thing that I don't know is the radius of the balloon is R,
Oh,
is big
okay.
R. So
Right,
I'm
and
assuming that's what I'm supposed to find.
Yeah, okay, that makes sense to me. Watch, let me see if this helps.
Okay.
And maybe this will jog some memories back to your calculus 150, which I'll just say last semester, but I guess I really don't know when you took calculus.
It was longer than that ago.
Okay, yeah. So, all right. So here's really the heart of your question. It's relative rates, and so let me start here. Let me go back to. I'll start with the equation for the volume of a sphere.
Mm-hmm.
Okay. And let me also point, well, there's a lot of places you can get it. I was about to say this is in the appendix of your book. And although that's true, in today's world, you probably have numerous access to it. So let me not worry too much about that. Okay.
Well, I mean, I know the volume of the sphere.
Oh, okay. So that's your starting point.
Okay.
All right. Here's where the calculus kicks in. And I'll just write it in kind of a weird way that I'm going to say, I'm going to take the derivative of this with respect to time. So how do things change with time? And I'm going to do both sides of the equation. Okay. Because again, from a math class, you know, what you do to the left-hand side, you have to do to the right-hand side to keep it balanced.
Mm-hmm.
But the key here is I knew to do a derivative with respect to time because they've given me information about the rate at which things are changing with respect to time. Okay. So before I actually do the derivative, let me come back up here. I deliberately did not say or give a symbol up here. This 666 cubic centimeters per second, you said in words. You said it was the rate at which the volume is changing.
Mm-hmm.
Fair enough?
Yeah.
So what could be a challenge for you, because I know it is for some students, is what does that mean in mathematical symbols? And this is what it means in mathematical symbols. It means
dV over dt, right?
Yeah, good. And so they are giving me dV over dt. They're giving me the rate at which the volume is changing. And let's go back to that first number you gave me, the 0.522 centimeters per second squared. You said that was the rate at which the radius.
That's dr over dt.
Right, so that's going to be dr over dt. Okay, good. So that's an important step that you seem to have a handle on. Now let me come back to this mathematics. Okay, so this side, which I'll call the left-hand side, would just come out to be dV dt.
Mm-hmm.
All right, and that's that 666 we just talked about. Now, when I take the derivative of the right-hand side of the equation, remembering from calculus, and you may or may not, so I'm just going to say that constants can be pulled out in front of the derivative.
Mm-hmm.
All right, so the 4/3 and the pi, I just pull out in front of the derivative.
Then
Now
3r squared.
The derivative of this. Now here's where you need to be careful. It's true that it's 2r squared, but
wouldn't it be 3r squared?
Thank you. My mess up. My bad. Yeah, 3r squared. But what can easily be forgotten by students is dr dt. This is the chain rule.
Right, because we have to take because the R.
Yeah, see if this picture helps. Do not confuse. If I have r cubed, and I'll do it twice, I could take the derivative with respect to r, or I could take the derivative with respect to a different variable.
Mm-hmm.
See, if it is with respect to r, this really is 3r squared. And we don't usually write the chain rule of dr because that's just 1.
Mm-hmm.
We just write it as 3r squared.
Right. The chain rule pulls out that the derivative, you have to take the derivative of the inside function. So you're
right.
getting,
If it's not the same variable, then we have to treat it like a composite function.
okay.
And you probably saw it in a math class that looked like this. If the function is f, and that function f is a function of g, so it's a composite function, and you take the derivative with respect to x, you then have the derivative of f with respect to the g, but then the g with respect to the x.
Mm-hmm.
So in my case, this f would be the r cubed, and I'm taking it with respect to r. And then I'm taking the derivative of r with respect to t.
Cool.
So that's how I would go from what you probably recognize from your math symbols to the symbols we're using in this problem. All right, so let me come back up then to this, and I can even keep going, but I think you'll now see that you were given this number. This is the dv dt.
Yeah.
So that's the 666.
Mm-hmm.
And you were also given the rate at which the radius is changing.
Mm-hmm.
The only thing that you don't know in this equation is the
big R.
And so now you can solve for R radius.
Okay.
And I don't want to leave you shortchanged, but are you good with that?
Yeah, so I just need to solve for the R there.
Yeah. But that's what's meant by relative rate. So what you would have on one side of the equation is the rate at which one variable is changing. And on the other side of the equation, you would have the rate at which the other variable is changing.
Mm-hmm. And so from here, it's just a matter of plugging in and solving for
Yeah.
R.
Yeah,
Cool.
now it's algebra. Yeah.
Awesome. That helped a bunch. Thank you.
Uh-huh. My pleasure.
Hi, Professor.
Hey.
Hi,
How you doing?
I'm in your beginning physics class.
Yeah, that's 102.
Yeah, 102.
Yeah.
And I'm just doing the lab right now. So I just have a quick question about graphing the average velocity.
Oh, okay.
If it's average velocity, does that mean that I put the dot in between like 0 and 1? So I'd put it at 0.5?
Oh, actually, yes. But you don't need to. That was something that I should compliment you on. That technically, yes, that would be a better way. It's not a necessity because they're asking for the slope, and so you would have the same slope. It would just shift the position of the line.
Uh-huh.
So that's why I, in the video and the book in the instructions, did not say to do it the way you're suggesting, but I would say what you're suggesting is a more thorough way.
Uh-huh.
But
Yeah, because it turned out a little bit strange. It's like there's like 3 dots, and then it goes up to another 3 dots. Like, so I don't know if I graphed it wrong.
Yeah, let's see. Can I make your screen? Oh, yeah. Yeah, I'm thinking there is something wrong with your graph.
Okay. Well, I can show you my data.
And oh, I cannot. read that. What if I go to speaker view? Say something real loud.
Hi.
Ah, much better. Oh, say it again because I lost it.
Hello.
Okay, lift it up a little bit. What's your last data? And say something again.
Hello.
Yeah, that data looks good. I think you just put it in the wrong spots on the graph.
Huh. Because I did 0.5 and then because the average between 0 and 1 is just 0.5. So then I did 0.5, 45. Then I did 169 because that's what it did. So maybe I should just try and regraph it. But my data looks good, right?
Yeah, your data seemed really good. I wonder if it's not too much to ask. Check your points on the graph because I really think something's wrong there. But let me come back to this computer. But if not, could you take a picture of those? And during the break, I can, look at those numbers. And
Okay,
compare.
so just email it to you?
Yeah, just email it to me.
You want the graph or the numbers?
Both would be helpful just in case, because the numbers seem okay, but, they could be wrong.
All right, I'll do that.
Yeah, okay.
Okay, other than that, thank you.
All right. Yeah, you bet.
Bye.
I have a question about I'm in your physics class 102, and I have a question about like the exercises and assignments and also the lab.
Yeah, good. Okay, go ahead, Oscar.
I'm wondering like, how do you want us to turn it into you? Like, do we take a picture of it and then post it on Canvas, or how?
Yeah, you're going to turn it in Canvas, okay? And you can either take a picture or you could do it in a PDF. It might be a little easier for you just to take a picture once you've done the work. But I know a lot of these, a lot of my students have this app that turns a picture into a PDF. And I only say that because on my end of it, Canvas handles PDFs really well and pictures not so well. But I don't want you to stress over making it a PDF. So if you know, I guess I'm saying is if you know how to make it a PDF, please do. That's helpful to me. But if you don't worry about that. Just do the homework.
I'd like send like 5 pictures, I guess, for the lab. Or...
Yeah, exactly. So the lab is, as you said, 5 pages. Mm-hmm.
And also for the exercises, you want us to do the same thing, right? We write it on a piece of paper and take a picture and send it. But would you like us to write down the questions for the assignments and then the answers under?
As far as rewriting the questions, no, that's not very useful to you. That's just a waste of your time.
Okay.
So don't rewrite the question, but when you do the answers, you can then upload them into Canvas. But you don't have to do them the old pen and pencil way, but I do think that's, pencil and paper way. But I do think that's best, only because that's what you're used to. So if you're comfortable with just taking a picture of it and then go to Canvas, I say that's good. That's what I kind of expect most people to do. Some people have scanners, so they're going to actually then print the lab manual, write it out, scan it, make it a PDF and send it, and that's good too. Some people are going to take a picture and then they have this little app that converts it. I should learn what that is so I could share with you guys. But
there's
that would
Adobe Scan that makes it a PDF, or what you could do is what I usually do is I just take pictures, put all those pictures in a Google Doc, and then turn that into a PDF. And so far.
Okay. I don't know if you caught that, Oscar, but if you just put your picture on a Google Doc, that makes it a PDF. Or some people aren't even using the old pencil and paper. They have either an iPad or one of these fancier computers where you can write on the screen. I guess it's a touch screen computer. And they'll do their homework right on there. That's a little more sophisticated. But what I'm getting at, Oscar, is it doesn't really matter to me how you do the homework. It doesn't really matter to me what type of file it is. And so the easiest answer is to say, just do them on a piece of paper, old school, take a picture, and upload it onto Canvas.
Okay, and also for the chapter videos, the lectures, do you post that on Canvas, or how do we find those?
Oh, have you been getting my emails? I don't
think I received emails for the second half of chapter 2. I just watched chapter 1, like on the email you sent, like for freshmen, and that it also came with half of chapter 2. And then
okay, so that was the email. So that was the email that said week 1 assignment, right?
Yes.
Okay, then last Sunday night, you should have got an email. I'm gonna write down your name here, Oscar. You should have got an email that said week 2 assignment.
Yeah, I didn't receive anything like that. I just found the second parts of chapter 2 on YouTube.
Oh, all right. Well, then I can see why you're kind of wondering.
For the textbooks, do you post links of it, or do we have to buy one?
No. Okay, so back to your week number 1, that assignment, that first email, you said you got the assignment for week 1?
Yes.
Attached to that email would be 4 important documents. One of them is the textbook. Another one is the lab manual. Another one is the syllabus. And the fourth one is the homework package, the homework you should be doing. When I'm on the break here, Oscar, I'm going to resend the week 1 assignments and the week 2, okay?
Okay.
Because you need those. Now, you said you got week 1, and those were the videos, and like I said, those should have, but I'm going to send it to you anyways. That has a PDF of the textbook. And then last Sunday, week 2, shows the videos that you're supposed to watch this week and, gives you the description. But you remind me of something I need to learn myself, that I want to put these assignments also on the Canvas page. I think that will give a one place that everybody can go to in case they misplace my email. But I haven't done that yet because the school, the way they set up their system, it's kind of weird. I only have 2 classes, Physics 102 and Physics 122. But when I go to Canvas, Canvas shows it as 13 classes. And so it's a management nightmare for me to try to paste this. But I know there's got to be some feature. And I think I told the group last week that I would try to figure out how to merge those together. Once I figure that out, I should really only have 2 classes, and this would be really easy. And I just haven't had the time to figure out that. So that's why it's not on Canvas, but that's going to change. But what you should really be looking at is the emails.
Hey, Professor, can we look at the chapter 24, problem 4, by any chance?
Yeah. Let me jump on that. Just want to double check with Oscar then. Does that make all sense, Oscar?
Yes, I think that's all. Is it okay if I can leave the call or no? Because that's all the questions I wanted answered.
Okay, so I answered everything.
Yes.
Okay, good. And feel free to when it comes to logistics, yeah, just send an email anytime.
So also the lab that's due this week is the motion one, right? And then next week it's vector.
The first half is correct. This week will be motion. Next week's kind of interesting. I'll look for my email Sunday night, but this is what I'll say Sunday night. I'll say that if this had been a face-to-face class, because Monday's a holiday, we wouldn't do a lab.
Mm-hmm.
So we're actually not going to have a lab next week. The vectors lab will be the following week.
Also, the videos we have to watch for next week is chapter 3, 4, and part of 5, correct?
I don't think we'll get that far. I need to look at it, but it will be the
At
rest
least
of
3 or 4.
Yeah, it'll be 3 and 4. Mm-hmm.
Okay.
Yeah. Right.
Well, that's all I need answered. So.
Okay, good. I'm going to leave this note for me, and I'm going to send you some more instructions by email, and also resend week 1 and week 2, and I read them, and I think that'll answer a lot of questions. And then just if you still have more questions, yeah, respond back. Either show up on a Zoom later on today or email me.
When do you have another Zoom later?
Let's see. We Zoom almost all day Friday. We Zoom from. Oh, and of course, that was another email I sent. I need to look up. If you're in class, because if you're not getting these emails.
I'm getting most of the emails. I got the email for the Zoom help yesterday.
Okay. So okay, good. So yesterday you should have got an email to me reminding you about these Zooms. And they are the first session we do here. So we'll go an hour and a half. So let's see, we started at 10. So we'll go 11 and a half and take a little break. Come back at 12:30. Go another hour and a half. So that'll be 2 o'clock. Take a break. And then come back at 3 o'clock. And then we'll go till 4:30, or last time I think we went over that, and just to make sure everybody felt comfortable leaving and moving on with the next week. So pop back in any of those times and look at that. Look at that email you got yesterday that says Zoom link, Zoom times. Okay.
Thank you.
All right. Great. Okay. I still can't pronounce it. I apologize. Time in. Hey, Dr. Young, go over chapter 24, problem 4, right?
Timmy, yes.
Timmy.
Yes.
Oh, good. You changed it in the spelling. I like that. Timmy. All right. Let's see. I'm going to write here. Okay, so chapter 24, number 4. Keep reminding myself what I'm doing. Plus, maybe somebody will be wanting to see these Zooms and maybe kind of flipping through kind of quickly, and they'll go, okay, which one are they doing now? Okay, so I need to come to your class. Okay, so 24, number 4. Let me scroll back up. Oops, wrong class. 24, number 4. Oh, here we are. So consider the closed triangular box resulting in a horizontal electric field of this. Calculate the electrical flux through the vertical face, and then B, the slanted face, and then the entire box. Okay. So there's a picture that looks, and I'm just going to do a cross section that has a vertical wall on what I'll call the backside, and then it angles down. And so a cross-sectional view is a triangle. Well, I said I would only do a cross-section, but maybe I should just at least give a little bit of hint towards the dimensionality of it. And some dimensions themselves. They say the height of this wall is 10 centimeters. They say the angle here is 60 degrees. They don't give a distance here, that's fine. And then they say that it has a depth into the paper of 30 centimeters. And I'll start then with A, probably the hardest one, which hopefully you'll see is not too bad. And it asks for the flux. As you, I hope, got out of this, is that the equation for flux is this. It says add up the electric field over some area. So this was Gauss's way of kind of visualizing how many little lines would go through a surface. And so if I kind of draw a setting of 4 of these kind of poking in here on the back surface, that's what we're asked to find.
So is the back surface actually a rectangle or triangle?
A rectangle, yeah.
Okay.
So the back surface, if I could kind of draw it, would come out, drop down like that.
So there's
And so
none of the electronic field is going through the triangle then.
So
In the
that red is supposed to be the back side. Okay, and then I'm sorry, ask your question again. You said something about the front side?
So the flux for the triangle in the front should be 0 because none of them are going through.
Correct, correct.
Yeah.
I don't even think they ask about that though, do they?
Oh, I read it wrong. I thought it was vertical triangle.
Yeah, no, B is asking for this. Hey, so let me just ask you, are you good with A?
Yes, it's really, I thought the answer was wrong and I got confused.
Okay.
Thank you.
So I had a quick question about A on this problem.
All right, should I keep going with A?
So, well, I didn't write down that step. I just skipped to the step EA cosine of theta.
Okay.
Is that okay?
In this case, yes, but remember, here's what you did. I'll do it in 2 steps. You first took the dot product.
Yeah.
Then you said, whether you realized it or not, and this is what I wanted to check, you said that the electric field is constant over that surface. That's the only way you can mathematically justify pulling the E out in front. So it is in this case. So that's fine. Just in other cases, that may not be okay.
Okay, but if it's appropriate to skip the steps, is it okay if we like on a test if I skipped these first 3 steps on this problem and just wrote EA cosine theta, would I lose points?
No, that's perfectly understandable. They're pretty straightforward tests. I mean, switch back so I can see everybody. Yeah, those are pretty straightforward steps that, yeah, I would say, well, yeah, they've done that so many times after doing the homework. They knew it, they just skipped over it.
Okay, and then I was wondering how the angle, the theta, is 180 degrees for part A.
Okay. So the angle that you talk about.
Yeah.
And so let me come back down here to the picture. So here's this red rectangle. The electric field is pointing in to this, what shall I call that object? It looks like it's a prism.
Oh, is it 180 degrees because we're finding the rectangle and the rectangle's angle is pointing straight up. So
So I would say the rectangle is pointing straight back in, I don't know, I wouldn't call it up, but
okay.
that red one would be the area vector pointing back, and the electric field is pointing in.
Okay. So
And
it's
so
basically
that's your 180
120
degrees.
plus 60 when giving you 80 or 180. Okay. Okay, that makes sense.
Okay. Yeah, so this just becomes, as you pointed out, the value of the electric field times the area times the cosine of 180 degrees. And of course, the electric field, I forgot what the number was, but the area then we could get from these dimensions, it would be 0.1 meters by 0.3 meters. And then there's our -1. And I know you're not asking, but I just out of my own, I guess, completeness, curiosity, let me come back and say, so the electric field they said was 7.8 times 10 to the 4th, and then so 0.1 times 0.3, and then times the -1 come out to be a -2,340. Let me switch over to the solutions. Is that what they got? 2,340, yeah. And then my units would be a Newton per Coulomb for the electric field, and then square meter for the area.
Okay. And I noticed they have theirs in kilonewtons. If we just wrote like 2,340 newtons on a test, would that be right? Or do we have to write kilonewtons like they have it?
Oh no, that'd be right. It's the same thing. Same thing.
Okay.
Yeah. Don't sweat over that. It would be like kind of the famous one. Is it 6 or is it a half a dozen? You know, well, same thing.
Actually, could you go over B as well? I don't know how to get the area for the slanted.
Oh, now wait a minute. I'm very glad you asked about B. I was hoping somebody would, and I was going to do it anyways because there is a temptation to do this the hard way. And what I mean by the hard way is to actually come back up here and do this integral. But one of the things I'm hoping you are getting out of this is a visual effect. And so you see all these lines that come in the back, they exit the slanted face.
Yes.
So the same number that go in, which we just calculated to be this, is equal to the numbers that go out. So all we got to do is say it's the same number but with a plus, because when they come out, they're positive. When they go in, they're negative.
Oh yeah,
Okay.
That's nice.
Yeah.
So I did it the long way. I just calculated it out, like, because I didn't see that. But I'll look out for that next time.
Yeah, you definitely should, because you will make the homework way too hard, sometimes impossible if you can't visualize it, and you will not have enough time on the test. So
yeah, definitely added a little bit of work rather than just that. But like if for whatever reason I don't see that and I do decide to calculate it out, I didn't
Okay.
understand why the width was 0.1 meters over cosine 60.
Oh, because the area would be of the slant would be the length of this guy. Okay.
Okay.
So let me call that L for a moment. And then let me come down here and do this. That I'll just draw cross section and call that L. And remember, this is 0.1, and remember this is 60 degrees.
Mm-hmm.
So cosine of 60 degrees is 0.1 over L. Rearrange it, and I get L is 0.1 over 60 degrees.
Oh, I see. So just some trig. Got it.
Yeah. Yeah,
Cool.
so it's doing a little trig to figure out what L is.
Cool. I'm gonna try practicing looking out for watching for equal amounts of electric field coming in and out.
Yeah, and watch C. Nobody's asked about C, but I'm going to do it anyways. C, let's see how they word it. C says the entire surface of the box. Okay.
Isn't it just the negative number plus the positive number, which makes 0?
Yeah, but without actually doing any math, I would do this. I would say, okay, what goes in the backside goes out the slanted side. Nothing goes in this front triangle. Nothing goes in this back triangle. Nothing goes in the underneath piece. Simply put, everything that goes in matches everything that goes out. Got to be 0.
Okay.
0.
That makes sense.
Yeah, if you spend more than 2 seconds on coming up with 0, you're missing the visual picture, and that's what I want to point out.
Yeah, I definitely need to practice looking at the visual picture more. Okay,
Well,
thank you.
That's why we're here. That's why we're doing the homework. Oh, you guys have engineering, huh?
Yeah.
Yeah. Okay.
I dropped that engineering class.
Oh,
okay.
I decided to stay another year, so I
Okay.
can focus on physics and math.
So, yeah, you're gonna have a lot going on. Okay, let's see. I'm gonna go to the chat here. Oh, thank you. Let's see. Ali, who said, say you can use Scanner app too. It's free. Yeah, I think that's the one that the school was emphasizing. Yeah. All right. Anybody want to jump in? Some of you just been hanging out. I don't know if you're watching or just kind of take anything, or if you have a particular one you came for.
I'm back.
All right, Timmy. Don't you have engineering?
I had engineering already.
No. Maybe we're talking about the different engineering. Which one are you in?
I'm not taking any engineering anymore. I'm taking CS and the physics. That's enough.
Yeah, true.
So for question number 21,
Okay.
I saw the answer was trying to use the E lambda thing, but I thought it was only for conductors. And this question, the sheet is not specified for being a conductor.
Oh, okay. Let's talk here. Easy to confuse those two. Let me read the question. Number 21, you say. A large, flat, horizontal sheet has a charge per area. What is the electric field? Okay, just above the middle of the sheet. Now, they did not specify in this problem whether it was a conductor or an insulator, did they?
No.
So that's too bad because that leads to some confusion. So I think though, sadly, yeah, this can get confusing about a factor of 2, depending on what they really mean. I think that's where you're struggling with, huh?
No, I don't get why we would use this equation since it's not a conductor. 2 I understand because it says it's above the middle of the sheet, so it's half of it. Or not.
It's no, the 2 is not because it's in the middle. Let me see if I can clarify this. In fact, maybe this will give me a chance to kind of review the derivation of it. Here's what was done in the book. If you take something that is this thin, infinitely long sheet, and I'll kind of draw in my picture a little bit of thickness so you can kind of understand my picture. That was a terrible line. But remember, it's just really, really thin. And so what they did in the book here, and what I want to repeat here is, if you're somewhere in the sheet somewhere. Now remember, this is really, really big. So in my picture, I've drawn edges just so you can kind of understand what I'm trying to draw. But you got to imagine there really are no edges. They go really far. So let me come right here, the middle of the sheet somewhere, and let me draw kind of a circle cutout. Because if you could imagine a Gaussian surface that looks like a cylinder on its side, okay? Well, in fact, let me reach over here and see if I can grab my sticky notes. If I kind of made a cylinder here and use the sticky notes here as the sheet, I'm trying to say, imagine this. Here's the sheet, and you're looking straight down on it, and I put this cylinder right in the middle. So the cylinder is going to be the Gaussian surface, and that's what I'm trying to draw here.
You're drawing it pretty good.
Oh, good, thank you. I was just about tempted. I could also go to the book and copy and paste it, but if that's not needed, I'll just stay here. Okay, all right. So if you visualize that, remember then the charge, and maybe I'll do the charge in red, is actually on the sheet. It's not distributed within that Gaussian surface. And so the process of finding the electric field in this chapter is learning how to manipulate this equation. This is called Gauss's law, okay? And this is, and this will be big for you, Daniel, to hear this, that when you go to solve these, you can make them really easy when you visualize the flux, okay? So if I had the electric field, I wonder if does drawing in pencil look a little different? Probably not than my black pen. But here's what I would argue, that the electric field coming from these charges would be going straight out from the sheet So it would be going through this surface here. Let me call it area A.
So it's starting out at the sheet?
Yeah, so coming back to here, the electric field would be pointing outward in a backwards direction. Let me put my let me point my pencil that way. And then on the front of the sheets would be pointing that way. And so what I'm trying to visualize or get you to visualize here is, and maybe I should draw the electric field in red. So it'd be going that way behind the sheet, and it would be going this direction in the front of the sheet. So if I hold this up here again, it would be going, I'll put my index finger, it would be going that way behind the sheet, and be going that way in front of the sheet. And so this right here would also be area A.
Okay.
And so
that makes
here's
sense.
that magical step. Here's where visualizing the flux comes very, very useful. If we call this side area 1, we call this side area 2, and we call this part, the part that wraps around in a circle, the part that, so this end of it, I'm calling area 1, and this end of the cylinder, I'm calling area 2, but this side that wraps around, this is, I'm going to call area 3. And no flux goes through that. So when you do the integral, you're really talking about the flux through the whole surface, all 3 surfaces. So surface 1, surface 2, and surface 3. That's what this little circle means in our calculus. It says add up the electric field over the whole surface, all 3 pieces that make up this Gaussian surface. And so maybe I should call this number 1, which would be the right-hand side, and number 2, the left-hand side, and number 3, what is often called in geometry, the face of the cylinder. See, and this
Wouldn't
way,
it just be 0 because
yeah,
they cancel
good.
each other out?
Oh, whoa. Okay, sorry. No, they don't cancel each other out. They're both going out. They cancel if the amount going in equals the amount going out.
Oh, okay, I see.
See, they're both going out. So the visual effect here is this then would be twice the flux from number 1. Because I think that's what you were saying. 1 and 2 are the same.
Mm-hmm.
But they're not positive and negative the same. They're both positive. They're both going out.
Okay, that makes sense.
Now, I hope what you also visualize is number 3. Number 3 would be 0 because it doesn't go in or out of this face. It's just poking out surface 2 and it's poking out of surface 1. All right, so now I'm going to, you notice, switch an integral that had a closed symbol, all 3 surfaces, down to an integral that is talking about just surface number 1. And this is that step you asked about earlier, Daniel, that I could, okay, this really is EDA cosine, and I'm going to put 0 degrees because when I look at this picture, the electric field is poking out. And remember, the normal is perpendicular to the surface. So if this is the area vector and this is the electric field vector, they're in the same direction. There is 0 angle between them. And so this just becomes E times A. where A is come back to the picture, A is that area of that cylinder. No, no, sorry, not the whole cylinder, just the, what I call number 1 area, the little circle. And if you look at the other side of this equation, which I haven't been messing with yet, so let's go back to the other side of the equation. This says this is the charge that is inside of this Gaussian surface. And if we come back to our picture, the only charge is right here. That little part inside that, which I guess, in this would be kind of like this little strip right there. Now that I flattened my sticky note. But as this kind of cuts through the middle right there, this is the only place there is charge. So what I could do is say, well, the charge inside would be the charge surface density, sigma, that's on here, times the area. And I claim that the area here is the same as the area there, right? It cuts through. And so if I took a slice, that would be the same area there as there. And so if I transfer that down to this line,
the areas cancel out.
and areas cancel out, I can use then Gauss's law to say that the electric field coming from something like this is equal to this equation. And so, Timmy, that's what this 1/2 came from.
Got it.
Yeah. And if this had been like a, conductor that the metal surface arced around, you wouldn't have had this piece. And so you wouldn't have had this factor of 2. And then you would have just had the electric field on the front side, and you would get a sigma over epsilon. So that's why I wanted to point out in this equation for you that be careful when you're looking at the electric field on a surface, because for the conductor, if they're talking about the charge on this, part of the conductor, there's no 1/2. But if they're talking about an insulator, or you might just say something that is so thin that it's like an insulator, even if it is a conductor, it would poke out in both directions, and you get that factor of 1/2.
Got it. Thank you.
So that's where I think your main question was, why did they use a 1/2? And I think because they're talking about a vertical sheet, it's very thin, and they're not distinguishing whether it's an insulator or a conductor at that point. Once it's so thin, the field goes both ways. But I think the problem would read better had they said this is an insulator.
You said the test is going to be open book, right?
Yeah.
Okay. Does that include notes and everything, or just the book?
It does include notes. Yeah.
Okay.
Yeah, and so when I send out the instructions for it, I'll say something like, it's open notes. Use the book. Use your own notes. You could even reference the videos, but that would be hard during a test because there's time pressure.
Yeah.
But those electronic notes I sent to you guys, those are good ones. So you can reference those.
Okay, so for the test, we'll be able to use anything we've had access to, basically.
Yeah.
Okay.
Yeah. Basically, it's, anything that you've created or notes you've done, just you can't use another person.
Yeah, that makes sense.
Or artificial intelligence like Siri.
Yeah. But you'll send out an email saying, like before the test, saying it's open book and open note, so that way it's in writing somewhere.
Yeah.
Okay. Cool.
Do we have enough time for one more? Or?
Oh, sure. Is it time already? Oh, it is. Okay, yeah, let's do one more and we'll take a break and come back at 12:30. Sure.
Can we look at 47?
Sure. Let me switch back. 47. Who said that?
Chase.
Chase. Oh, I see you. All right, Chase.
I have to go do some things. I'll see you in later sessions today, Dr. Young.
Okay, looking forward to it.
Bye.
Okay, so chapter 24. And you said 47?
Yeah.
Okay, let's me read 47. Here's a good one. Yeah. Okay, so.
And I got the first three in part A. I was just really asking about when R is greater than C in part A and then part B.
Oh, okay. So let me try to draw that picture here. So here is the inner sphere, which they call an insulator. Then there's a little bit of gap in space, and concentric around it is a conductor. And the outer radius of this conductor is C. And you're asking about the last half of A, which says R greater than C. Okay. I'm going to then draw a Gaussian surface around on the outside, because that's where they want us to find it, R greater than C, and then do another calculation of Gauss's law. And although I didn't draw my circles very well here, I'm hoping you will see that when you take this dot product, E dA cosine theta, and if those other inside pieces made sense, and if my lectures made somewhat sense, you could argue by symmetry that the electric field is the same. Whoops, I messed up there. The electric field is the same everywhere on this Gaussian surface, so I can pull it in front of the integral. And the angle would be 0 degrees everywhere on this surface. And of course, cosine of 0 degrees is 1. And then you reduce that integral to just the surface of this Gaussian surface. So this becomes E, and the area then of a sphere is 4 pi r squared. So that's the left-hand side of R1. Then this side is actually, in theory, the easier side. This just says all the charges inside. Well, all the charges inside would be the charge on the insulator plus the charge on the conductor. And here's where I'm going to have to come back and read it, because it says a solid insulated sphere of radius A has a uniform charge density of rho and a total charge of Q. Okay, so I'm going to put a Q inside here, because they say Q is the charge inside that insulator, concentric with a sphere that is uncharged. Okay, so 0 charge on here. So when I add those two together, I just get Q. Q is the total charge. And so the electric field then would look like that for R greater than C.
All right, that's what I thought. It was just the conductor that was throwing me off. I didn't know if that changed anything.
It changes a few things, but not the field on the outside. Let me draw another picture, because you're right. This always throws people off. Here's what it would here's what it would look like. You would have this charged object. Let me just put a bunch of pluses. And then you would have this electric field going outward. And you must know the answer to this one because you didn't ask it. But the field inside the conductor, so when the radius is between B and C, would be 0. So what would happen is on this inner surface, and because it's a conductor, negative charges would move to the inner surface. But of course, they do that by leaving positive charges on the outer surface. Because remember, this conductor has to have a 0 net charge. So it's these negatives that then terminate or stop the electric field. So that's why you get 0 electric field in here. But now you have charges on the surface, and so the electric field continues on, and it's the same amount of charge that terminated them that restarted them. So that's why this field out here actually has the same equation that if you never even had this shell around it. And that's, I think, why it was confusing you. You're like, wait a minute, that's the same equation I would have gotten if I didn't have this shell around it. And you're thinking that shell should have done something. And it did do something, but it didn't do anything out here. What it did is made a 0 field in this region of space.
Okay, yeah, that's what I was thinking.
Okay, so good. And so I just added that for you and anybody else who needed that. It says here now, oh, see, now it says determine the induced charge per unit area on both the inner and the outer surface. So I'm glad I kind of explained all that, because in order to terminate this field, since the field coming from the insulator was created by all this charge Q, on the inner surface, there must be a negative Q to terminate it, which means there must also be a positive Q in order for the total charge on the conductor to be 0. So if I was looking for, let me just read it here, it says determine the charge per unit volume. So they're after the sigma, and I'll say on the inside piece, but they're also after the sigma on the outside. So on the inside, the charge, as I just mentioned, is a negative Q. And on the outside, the charge is a positive Q. Now, there would be a little difference because the surface area on the inside piece is 4 pi over r squared. And the surface area on the outside piece would be 4 pi over c squared. So there is a different radius for the inside piece and the outside piece. And so what's different about these charge densities is, number one, and the big one, is the sign. Inside is negative, outside is positive. But another little subtlety is they have a different radii.
So it's not a volume, even though it's a sphere.
No. Where the charge is on the surface. And the problem even says the induced charge per unit area.
Oh,
So the charge is on the surface.
because it's a conductor. Got it.
Because it's a conductor. Mm-hmm. It makes no sense to talk about the charge per volume for a conductor, because inside the conductor, right there, that little chunk inside the conductor has no charge density.
Yeah, okay. That makes more sense. Thank you.
Yeah, these are good ones. All right. Okay. Well, let's take our break. What looks like I'm looking at 11:41 here. So come back in 49 minutes, and we'll pick up. Take a little break. Walk around, stretch your eyes. In my case, I need to get something to eat and use a restroom. So I'll do that too. And see you in 49 minutes. How do I exit here? Stop sharing.